Okay, we're rolling. Here we go. So I gave you this situation, and we got a discussion going, and what we learned in that discussion was there was different ideas that were correct. Okay, so the first way that some of you might have made both bars a time bar. So here I'm saying that the bottom bar is the time to travel 72 miles an hour, and the top bar is the time to make the entire trip in hours. Okay, so I want you to quickly label these bars in terms of their values. Okay, label these two bars in terms of their values given this situation here. Let's start with the bottom bar first. The time to travel 72 miles. What would that be? That whole bar is 1 hour, right? And what about the top bar? 4.6, okay? And so where do we see scaling in this situation? What is being scaled? What is being scaled? It said multiplication is about scaling. Where do we see scaling here? So nothing to do with distance, right? And this represents, there's no distance here. So time is being scaled by what scaling factor? 4.6. We had 1 hour and we scaled it up to 4.6 hours. Is it okay? So that's something you could have done based on the situation I gave you, and that would be valid. Okay? Same thing with distance now. So how about the distance covered in 1 hour and the distance of the entire trip? What's the distance covered in 1 hour? Distance for the whole trip. So I'm not looking for a final answer, but what would it be? So, what is the scaling factor? 4.6. We took that distance of 72 and we're saying, okay, instead of 1 hour, we want 4.6 hours. So we're going to scale it or multiply it by 4.6. Is it okay? So first one, time gets scaled by 4.6. Second one, distance gets covered by 4.6. All right, well then we talked about one time and one distance. So the time to make the entire trip and the distance of the entire trip. What was the time to make the entire trip? 4.6. And the distance of the entire trip? 4.6. Okay, and so I think in our discussion what we said was, here, the time is getting scaled by 72 to give us a distance. We said the time is being scaled by 72 to give us distance. That's not really right. Because what would it mean to scale 4.6 hours by 72? We were scaling it. The result would be what kind of thing? Hours. Okay? So scaling is when we're resizing one quantity. So if we were thinking about this in terms of scaling, then would be hours, and that's not right. So this is a different thing going on here. And this is about what we're going to call constant multiple, as opposed to scaling. So what did a constant multiple do? It took the value of one quantity and it gave us what? When we multiplied by the constant multiple, it didn't give us a bigger version of the original quantity. Instead it gave us it gave us the corresponding value of the other quantity. See? So 72.4.6. Now that's the value of distance corresponding to 4.6. So it's not scaling. So we need to talk about it some other way. This is constant multiple. Now, but scaling is still part of this. Scaling is still part of what's going on here. We can actually see scaling in this diagram as a combination of both of these. In the bottom bar, we could talk about 1 hour, and that gets scaled up to what? 4.6 times 4.6. And in 1 hour, how many miles did we go? 72 miles. And so in order to get the number of miles for the whole trip, we would scale it up by 4.6, you see? So you have 72 in 1 hour, scaled by 4.6 would give you the total distance. But going between quantities is not scaling.
going between quantities is this idea of 72 as a constant multiple. Given the amount of time, multiply by 72, it gives you the corresponding distance for that amount of time. Does this make sense? So the multiplier 72 is from one bar to the other because these are two different quantities. Scaling is seen in each individual bar. 1 hour is scaled up by 4.6 to make 4.6 hours. 72 miles is scaled up by 4.6 to make the total distance in that time. Okay, so let's just summarize that. So given the value of the quantity, scaling is about resizing that quantity to a new value. That's what scaling is about. So if we were showing scaling in this diagram, we'd have 1 times 4.6 is 4.6. And 72 times 4.6 gives distance traveled in 4.6 hours. That's scaling. All right? Constant multiple is about finding the corresponding value of a different quantity. So here I am at 4.6 hours. Now I want to know how far did I go in that 4.6 hours. To do that, I would multiply by 72. Okay, anybody have a question about that? So, the goal isn't that I can explain that. The goal is that you can explain that. And so we'll do our best to get you practicing that in this very awkward environment for that, right? Lots of you packed in. But so the goal is that you're able to explain things like that. And not just say, listen and say, I get it, okay? All right, so now we had some Google class on Friday. You had homework. And we revisited this problem from Friday. So math 270 so far. How many of you feel like this? What's the deal with this, right? It's not like, is this really a math course, right? Well, I want to take some time to kind of prepare you and to give you an overview of what this course is like and why it's like the way it is, okay? So let's get a perspective on this. So first we want to talk about context, math education here in the U.S. and in other countries, and then let's do an overview of our course just briefly, okay? So in 1975, here was the natural science and engineering degrees for 124-year-olds. How's the U.S. doing here? If we think that's a valuable thing, to have lots of people in engineering and science, right? How are we doing in 1975? Pretty decent. How are we doing in 2000? Okay? Towards the bottom, right? So what's happening? So in the United States, what's the stereotype about mathematicians, scientists, engineers? What's the stereotype?
Geek.
Right? Geek, nerd, not cool, right? And so and these cultural things play into this. But also, the classroom culture has evolved over several decades into something that's resulting in less interest in math and science and less performance, lower performance in math and science. But, the internet age, people work from home, they do all their work over the internet. So any company that hires you, is competing with students from all countries all over the world, okay? So it's important that we can compete, that we have the aptitude to get jobs in in the information age. All right, so there was a study done where they randomly selected 8th grade classrooms in Germany, Japan, and the US. And they took the videotape lessons and they made written transcripts. And they took all of the and identifiers out of those transcripts. So if you were reading the transcript, you'd have no idea which country the transcript was from. And so they had outside people reading all these transcripts and scoring them for high, medium, and what they call high, medium, and low quality instruction. So in terms of coherence, significance, things like that. So in Germany, they were about a third each. Japan had more high and medium and less low. So I want to ask you, in this study, what percentage of class time did the U.S. have with what they deemed high quality instruction, and what percent was deemed low? What would you think? What would you think? Worse, okay? Worse. So the question is, what's going on in the classroom? Like what do we mean by high quality instruction or low? What's going on in American classrooms? What are the tasks and activities that teachers are having students do that are qualifying for basically all of class time? What are we talking about there?
Basic.
What's that?
Very basic.
Very basic, okay.
Well, it's more about the type of stuff they have you do. For example, in math class, they shove all these formulas into your head, and they're like, okay, there you go.
Okay, so it's very formula driven, okay?
They don't teach you why.
Don't teach you why. Cool, right?
It's very structured. There's not a lot of area for people to be creative about how to solve their own problems.
Okay. Other.
It's more about memorizing rather than actually learning.
Okay, so lots of you are hitting on the main points here. Memorizing procedures. How many people have had a math class where you basically memorize procedures? Almost all of you, right? That's low, because you can learn how to do these procedures and not really understand or know anything. And then if you get a problem where the procedure doesn't fit, well, you can't do anything, right? So you're not able to make any headway. Okay? So a lot of memorization, rule following, pushing the symbols around on the page without ever asking what it all represents, what it all means. Okay? So, is the calculus the same thing? How many people know about this? So we can do complicated procedures, put in some problems. Here's a calculus problem. What is the integral of sine x cosine x from 0 to pi over 27, or pi over 2? Within moments, it not only gives us a nice picture of it, it gives us an image, and it goes on and you keep going down the page, and it gives us all this information about this problem. It gives us the answer right away. Graphing calculator, which hopefully you've all downloaded by now. Here's another calculus problem, the derivative of x to the 3 to the x. It's a very complicated derivative, and we might spend half a class learning a procedure and learning how to find this derivative. In moments, graphing calculator just tells you the answer. So we have this technology that can just do it for us. So this used to be important. People learned calculus to get jobs they do lots of computing. Okay? They needed to be super fast at performing these procedures flawlessly because we didn't have that technology to do it, and we needed to get done. Okay? So then it was very, most people using calculus were given functions and equations. Their job was to do with them what they were told. Okay? But today, computers can do this in instants, right? Computers can just do this. And faster and far more accurately than a human can. But the computers can't decide what function to analyze or what equation to solve. So there has to be someone who's putting these things in the computers in order to model situations correctly. So a human must decide these things in order to tell a computer to do them. So in other words, users of calculus today are more like managers. Managers, okay? So in a restaurant, if you're the waitress, you just need to know your job. But the manager has to know everything about the operation of the restaurant, right? They have to know what the bartenders do, what the cooks do, what the hostess does, right? So they have to know the whole system together. And so that's what That's what it's like for us today. So you need, if you're using calculus, you need to understand what you're doing. And then you need to be able to explain why you're doing it. Okay? So, what's your past experience in recent math courses? So reflect honestly. When you worked with the symbols and performed computations, to what extent did you really understand what was it all represented? Okay, so this class is about developing an expert knowledge of calculus so you can figure things out, not just remember what you should do. Okay, so our goal is that you have a toolbox to attack any problem, not just some certain sets of problems that we're going to teach you how to do. So you have a toolbox of calculus so you can, in any situation, you can make headway and lots of progress. Okay, so for those who've had calculus before, it may be the hardest for you if you've had calculus before, because you're going to have this temptation to anticipate what I'm about to say, because it kind of looks like what you did before. Don't do that, okay? So just pretend that you didn't have calculus before. Try learning it with understanding and meaning. Don't try to guess where I'm going, because that will just cause you to tune out, okay? All right, so the moral is that good math instruction in the U.S. is not good by international standards, and I'm trying to awaken you to expect something much different here. So it's going to be different. Okay, so let's see how some students, past students, so what this class is not about. So talking about expectations. It's not about rote memorization, replicating examples and procedures, doing without thinking to get answers, or guessing what I want you to say. It's not about that. Okay, what it is about. Using your uniquely human capacity to think in order to understand the ideas, develop insight into quantities and relationships. Okay? See ideas coming in groups, not just isolated sets of problems. Okay? So we have a goal here. See the course as an endeavor for coherence of all of its ideas. All right? So most of what we do all semester will be to understand this, the fundamental theorem of calculus. So there's a journey that we're taking with a final goal, a final destination. It's not just learn how to do all these different sets of problems by mimicking procedures. Okay? So let's see a couple students and how it went for them. So a tale of two students. First student. Rate my professors. He's honestly a terrible teacher. Nice person. He tries to teach the why and forgets about the how. It really kills your grade. I never had below a 95 in math class, and now I'm hoping to get an 88. Okay? So what's really going on here? My belief is this student came to class with a set of expectations about what a good teacher is. And what was that set of expectations? This is my belief. Reading this. A good teacher demonstrates and explains complicated procedures really well, and then assigns grades based on the ability to mimic them. That's what I read here. And I might be wrong, but that's what I'm seeing when I read this. That the student had rock-solid expectations, and I was unsuccessful to change those expectations. And so, toward the end of the class, this is where he landed. Okay? But this is the kind of instruction that puts US near the last among other countries. This kind of explaining complicated procedures, mimicking them, where the US is. So trying to do something different, hopefully something better, that makes you more marketable in the world market. Okay, another student. There's an email she sent me. The first 4 weeks of class, I left every day feeling that my brain had been mauled into abstract obscurity. I was actually helping my friend from another college. She was amazed at how much I knew. Even though all of our language was different, I was able to teach her why each piece works, what it was there for. I have also been helping people at my table from class, homework. It's so satisfying to be having these daily aha moments finally. Okay? So what does this tell me? It tells me that even when there are expectations from the past, that you can make a journey. You can make a journey and you can transform your thinking and succeed if you work at it. Okay? So, when posed a problem or question or problem, expect to have to rely on understanding. Okay? Rather than an example or procedure to mimic. Okay? We want to bring together multiple ideas. We want to transfer knowledge from one situation to a new situation. And then we want to write coherent explanations of our thinking. And then when you come for help, either to the TAs or myself, rather than us doing it for you or telling you the answer, maybe we'll ask a question back to you to find out what you're thinking and help improve your thinking, okay? Maybe we'll give you a hint. But so many tutors on campus will grab the paper from the student and just do the problem and hand it back to the student and say, do you get it? Do you see? And this is not helping. This is not helping you. It's not helping you. Okay? So we're going to always be challenging you to think, and you make that journey from what you understand to what we're trying to teach. Okay, in terms of grades, by the way, in the previous fall semester, here were the final grades in my course, which is very comparable to other Cal courses taught in a more traditional way. Okay? So if you work hard at it and you put the time needed outside of class, you can achieve the grade that you want. And I would guess that student got an A. He thought he was getting an 88, but I would guess that he was doing better than he thought. Okay? Here's the moral. You're going to have to work hard for learning to be meaningful. Okay? It's not just going to come easy. It takes patience and perseverance. The benefits are great. Okay, so let's quickly talk about calculus. There's two fundamental properties that calculus addresses. You know how much of something there is, and you want to know how fast it's changing. So you have the amount of a quantity, and you want to know how fast that quantity is changing. And then the other is just really the flip side of that. You know how fast something is changing, how fast a quantity is changing, and you want to know how much of it there is. All of calculus is pretty much about one of these two things. So the first one is called differential calculus. The second one is called integral calculus. And so they're really two sides of the same coin. Differential calculus, you know how much of something you have, and you want to know how fast it's changing. Well, those changes accumulate at a certain rate. That's what you're trying to find out. But it's at that certain rate that they're accumulating. So this really points at integral calculus, and the other way around. If you know how fast something is changing, and you want to know how much of it there is, well, you have to see it as building up in bits at a varying rate. And so that's really going back to differential calculus. And so this is just really two sides of the same coin, one idea, which is rate of change. So this course is about rate of change. Okay, so let's pick up where we left off. We said that if we want the relative size of one quantity in relation to another, we're going to perform division, right? We're going to perform division. So a car traveled at a constant speed. It traveled 1829 feet in 19 seconds. How many feet did it travel each second? And so many of you, you've got a formula in your mind, and you've already got the answer, right? So let's kind of spell that out and use our bars to do that and to see what this all has to do with speed, okay? So how can we use the bars to figure out how many feet it traveled in 1 second? What would we look at first? Idea? Okay, so he wants to take the 19-second bar and divide it up into units of 1, or 19 parts. Okay? All right, so 1 second. So what is 1 second relative to 19 seconds? What is 1 second relative to 19 seconds? 1/19. So we can think of that 1 second as 1/19th of 19 seconds. And how does that, so then what, so if we want to know how many feet we go in that 1 second, what will it be? 1/19th of 1829. And how do we find 1/19th of 1829? What? Division, right? So the car traveled 1829 19ths feet every second.
I have a question.
Yeah, please.
So there's really not a difference from multiplying by 1/19 and dividing by 19. So like what scaling by 1/19 or dividing?
Yeah, great question. Okay, so he's seeing this. So he's saying we can think of this as multiplication or division. So as multiplication, it's scaling 1829 by 1/19. Is it fair? Yeah, that totally works. Okay, but so now we're transitioning to talking more about division. So scaling by 1/19 is equivalent to dividing by 19. Yeah. So yeah, both. But so if we're focusing on division, but I would guess that most people, when I ask the question, how fast does it go every second?
Yeah, they divide.
Divide, right? Divide. And so that's why it's divide, because that's how you get 1/19th of 1829. You divide distance by time. Okay, so someone put that in your calculator. When you divide 1829 by 19, what do you get? Equals what? $96.26. Okay? So if it's a quotient, if that number is a quotient, then somehow that quotient can be thought of as what? What idea or concept can you think of 96.26 as? That's a quotient. What did we say a quotient represents? Relative size. Relative size. So I want you to have a conversation with the person next to you. If 96.3 is a quotient, how can it be thought of as a relative size? Go. How can it be thought of as a relative size? Okay, so I'll start you out. 96.3 is the size of, if you're explaining it as a relative size, how would you finish the statement? 96.3 is the size of what? 1/19 of 1829. So we're not asking about the calculation, I'm asking about the quantities involved. Yes?
I would describe it as the ratio between the two quantities, the relation.
Okay. So what does relative size mean? We've got to get at what does relative size mean? Yeah.
96.3 is the size of the total distance traveled in comparison to the distance traveled in 1 second.
Okay, almost. So he's comparing it. He's saying it's the distance traveled the whole time compared to the distance traveled in What'd you say?
1 second.
1 second. Yeah, that's pretty good. Anybody else? Okay. So it's the distance traveled, the total distance traveled relative to the distance traveled in 1 second. Or distance traveled relative to an amount of time that goes by. So for any amount of time that goes by, the distance traveled will be 96.3 times as much as that. Well, that's really also like constant multiple, right? The distance traveled. So these are like, they're a little bit different, but so close to each other. The distance traveled always equals what? 96.3 times time that goes by. So that's thinking of that 96.3 as a constant multiple. It's taking the time that we have and giving us a distance, right? We said it gives you the corresponding value of a different quantity. As relative size, it's almost the same but a little bit different. So as relative size, it's how much distance is traveled relative to how much time has gone by. It's always 96.3 relative to how much time has gone by. Okay, so let's put a twist on this. So a fast plane travels 4,012 feet in 0.02 seconds. How far would it travel in 1 second? Okay, so see if you can use bar diagrams to answer this. See if you can make headway in this. Take a minute, go. So just so we're consistent here together. All right, what is our time bar going to represent to make this work? Now we're going to make this 1 second. So just from the beginning then, what's the length of the distance traveled bar? 4012? We don't know. That's what we're trying to find. The corresponding distance to 1 second. Okay? Now what? Yeah?
We could break the second bar down into tenths of a second, and then from there break that down into
We really need to break it all the way down to what? These, right? Really small. We really want to know what fraction of 1 second that is. What is it? 50th or 500th? And we know how far it went in 0.02 seconds, right? The corresponding is 4,012. far did it go in 1 second?
Times by 500.
So the question is, do we still divide? Do we still divide?
Well, you could, yeah.
So we're thinking about it as multiplying by 500, right? Because we need 500 of these 0.002 second increments to get up to 1 second. So we need 500 distances of 4012. So we really can't avoid thinking about multiplication, but can we divide? Yeah. Because multiplying by 500 is the same as dividing by 1/500. But in this particular case, we really have to, as we're thinking it through, it requires multiplication to get us there. So some big feet per second. A lot, right? Really far. So, do we still divide? Yes, we still divide. To think it through, though, we need multiplication somewhere along the way to make sense of it. Okay? But yes, we do still divide. Okay.